Welcome to section 3.4, which is called the chain rule. The chain rule is the third really big rule with the product rule and the quotient rule, which allow us to kind of find derivative of complicated functions that have, well, products, quotients, and here, compositions. So we are going to focus on that today. So we'll do the chain rule, then we'll talk about ways to simplify the algebra, then we'll talk about the natural log, which is one of the parent functions we haven't touched on yet, and then the derivative of exponential functions, which are not e power x, but a power x. So what does the chain rule look like? Again, it's used when you have a composition of functions. So for example, y equals sine of 3x, y equals e to the power of x squared plus 4. So this of, like when you put functions inside functions here, square root of sine of x. What does it look like? This is a composition of function. This is a composition of function, and we take the derivative of that composite function. And so what you do is you first take the derivative of the outside function and keep the inside as it is, and then you multiply with the inside derivative, so the derivative of the inside function. That part here, it's extraordinary how often we forget to multiply that. So be aware, this is maybe the number one mistake students make. If we just add all the mistakes in a year, forgetting the inside derivative might be number one in the entire year. So first example, what's the derivative of y equals sine of 3x? Well, here there's an inside derivative 3x, and there's an outside derivative sine x, or sine. So first we take care of the outside. It's going to be cosine of the inside. We keep it as is. And then we multiply by the derivative of the inside. So derivative of 3x is 3. When I said we forget the inside derivative, if the question is like this, you're probably not going to forget the inside derivative because this is what we're focusing on. We tend to forget the inside derivative when the exercise is about something else, and you have to remember, oh, here's a composition of functions. So being very aware of what the function looks like is really important. Second example, what's the derivative of the square root of sine x? Again, we're first going to rewrite this as sine x to the power of 1/2, so we can use the power rule. And this 1/2 is outside, and then the inside function is sine x. So first, let's take the derivative of the 1/2. It's going to be 1/2 times whatever was inside to the power of 1/2 minus 1. And then we multiply with the inside derivative. So here's the answer. There's not much we can simplify. This chain rule continues like that, even if we have a composition of 3 functions. So here there's a cosine of tangent of x squared. So you just go gradually. It's like peeling an onion. First you take the derivative of cosine, then you multiply by the derivative of tan, and then you multiply by the derivative of x squared. So let's see that. Derivative of cosine is negative sine. You keep the inside as is. Then you multiply that by the derivative of tan, which is secant squared, and you keep the inside of that part as is, x squared. And then you multiply by the derivative of x squared, which is 2x. And you stop here, because there's nothing inside there, right? X squared was the last step. Here, another example, which adds a little complexity. This is a composition of function because you have x squared, and then inside you have that. So first we have to take care of differentiating the square, and that becomes 2 times whatever was inside. 3x minus 1 over x squared plus 3, and then we multiply by the inside derivative. But we have to pay attention. This is not just any inside derivative, it's a fraction, it's a quotient of function, so we have to use the quotient rule. And the quotient rule is u prime v minus uv prime over v squared. So we set up u, v, u prime, v prime, and we plug in everything. And here, we could stop here. That would be fine. That's an acceptable answer. Or we can clean things up a little bit if we want, or if the exercise was going further, if there was another question, then it can be worthy of simplifying. But if the question is just find y prime and there's no specification, you can stop at the first line. The exercise below, sine of x times cosine x. It's a little bit the same. It's a composition of function, but you can see that the inside part is a product, so we're going to use the product rule. So outside sine and inside is x times cosine x. So first, let's take the derivative of sine. It's cosine of x times cosine x. And then we multiply this with the inside derivative, and it happens that the inside derivative is a product of x and cosine x. So I set up u equals x, v equals cosine x, and we proceed to writing the answer. So the derivative of ln is something we introduce now, but we'll talk about it more and prove it in the next class. The derivative of ln of x is 1 over x. And how do we use that in an example like that? You can see that we have ln of something. So we could use the chain rule. It would make perfect sense to use the chain rule. However, ln is a little bit special. You don't have to use this special quality of log functions, but it can be really worth it. If we just use what we've learned in 3.4 right now, we would do the derivative of ln, which is 1 over whatever's inside, just like here, 1 over x, because it's ln of x. Now it's 1 over that thing, because that's what's inside. And then we would multiply by the inside derivative. But this could be a little bit tedious, the inside derivative. We have a square root, it's a quotient, there's just a lot of things. It could be hard, or maybe not, but it could be hard. So, with logs, we can use the properties of logs first. In Algebra 2, you've probably learned these 3 properties. They are useful anytime you have a log. What they say is if you have the log of a times b, you can write this as log a plus log b. If you have log of a over b, you can write this as log a minus log b. And if you have log a power b, you can write this as b times log a. It was very useful, especially in the times before calculators and computers, because this is a multiplication, this is an addition. So every time you can change a multiplication to an addition, you can feel like it's going to be easier. Here you have a division, could be hard to do by hand. Here it's a subtraction, so that's much easier. So logs were highly, highly appreciated before the 20th century. And here you have a power, so this power you can also make it easier, and now it's a product. Multiplication is easier than a power. So if we apply these rules, the ln of this a over b, if I can say, can be written like this. It's ln of the square root of x plus 1 minus ln of 2x cubed. So I'm applying the second of the 3 rules that I just boxed. And here I can go further. I could even go further than I did, but I just took the square root as being power 1/2, and I brought it in front as 1/2 ln of x plus 1. So I'm using the third of the rules. So you might feel like, oh, this 1/2 came in front, isn't that what we do with derivatives? Well, somewhat, but it's just absolutely unrelated in this example. Here it's just a property of logs, and it happens to look a little bit like the power rule, but it's unrelated. We could have gone further. I could have separated this 2 times x cubed using the first rule up here. Somehow I didn't, because I felt like this was enough. It would become easy from here on to differentiate, but you could have definitely gone further, and it would be great. So what's the advantage? Well, now taking the derivative of this is going to be much nicer than taking the derivative that we started earlier and gave up on. The derivative of 1/2 times ln of x plus 1 is just 1/2 times 1 over x plus 1. This is the derivative of ln. And then we could say that we have to multiply by the inside derivative, but this is just times 1. The derivative of x plus 1 is 1. So we don't have to put it. Minus the derivative of ln of 2x cubed is 1 over 2x cubed times the inside derivative, which is 6x squared. So conclusion from this exercise, sometimes logs, using algebraic rules for logs, can be useful before using calculus. Okay, derivative of a power x. This is similar but not quite the same as e power x. What is the derivative if f of x equals a power x? Here's the answer. F prime of x is equal to a power x times ln of a. And we're going to see why this is true. This is a very elegant proof, not necessary in AP Calc AB, but if you spend the next minute and a half with me listening to what I'm saying, you may find that it's very elegant. It has a very clever idea. So the first step, which is the clever step, is to rewrite a power x into something equivalent. And this equivalent thing is to say that it's the same as e to the ln of a power x. Typically, when we have e to the ln of a power x, we just cancel e and ln, and now you can see, oh, this is equal to e power x. In this exercise, we're doing that backwards. We're kind of adding this e to the power of ln of a power x, but it's the same as that. And now, using the third property of log, ln of a power x is actually equal to x times ln of a. And here we can use the rule we know for e power x and the chain rule. We know that this is the outside function and that is the inside function. So what's the derivative of e power something? It stays whatever it was, so e power x ln of a, and then I have to multiply by the inside derivative. What's the derivative of that? That's tricky for students. The derivative of x times ln of a is actually ln of a. It's surprising, but think about it. Ln of a is just a number. It's a constant. I don't know what it is. Maybe it's 3.28, let's say. The derivative of 3.28x is 3.28. This is not a log function. It's just a number, ln of a constant. So it's a constant. And therefore, the inside derivative is just that constant. And finally, in the last step, until we reach this a to the x ln of a, which we are trying to reach, we are using this part and going exactly backwards from what we've done above. You can see that here we went from a power x to this thing, and now we're just doing it backward. We know that e to the x ln of a is just equal to a power x. So that's the answer. If f of x equals a power x, then f prime of x equals a power x times a certain constant ln of a. A quick example that requires the calculator. At what point on the graph of y equals 2 to the t does the tangent line have slope 21? Okay, so we are wondering about the slope of this graph, and we are wondering when it's equal to 21. So we're going to take the derivative of y equals 2 power t, and then we're going to set this equal to 21. So the derivative of 2 power t is 2 power t times ln of 2. This is what we just learned now, and we set this equal to 21. And then we solve for t, so that's just a few steps of algebra. 2 power t equals 21 over ln of 2, and we find t equals 4.921. If I round to 3 decimals, it's 4.921. But we were asked to find the point, so I need to find the y value. And the answer is here, 30.297. Now, something's interesting here. If I remember that x equals 4.921, and I write what was it, 2 power 4.921, I get 30.297. 294 or for 30.295. You're allowed to round or truncate. Rounding means this would be 295. You're also allowed to truncate, which means you just stop after 3 decimals, no matter what the fourth decimal is. But compare this to 30.294. This is not what I wrote here. I wrote 30.297. And in fact, 30.297 is correct. So what's wrong? What's wrong is your final answer needs to be correct to 3 decimals. Here, if we round here to 3 decimals, 4.921, we're making a rounding that's too early, because now I'm using this rounded number into a further calculation, and my rounding is just going to expand, and my 3 decimals are not going to be correct at the end. So that's an important thing for calculator. It's not important in the history of AP Calc AB, but when you use a calculator, you have to keep that in mind, that even though your final answer needs to be 3 decimals, any intermediate step, you should always keep 5, 6, or 7 decimals to make sure that you have the correct 3 decimals in the very end. All right, last of the derivatives of parent functions, what's the derivative of log of x in base a? So this is a special case of ln of x. Oh, well, it's the general case of ln of x, but it's not the natural logarithm, it's any logarithm in base a. And the answer is 1 over x times ln of a. So if this was the natural log, it would mean the base a would be equal to e. And we can check that if we use this general formula where a equals e, then the derivative is 1 over x times ln of e. ln of e is 1, so it works. It confirms that the derivative of ln of x would be 1 over x. The next example is it's a difficult but very nice exercise. At what point on the graph of f of x equals ln x does the tangent line go through the origin? In class, I usually ask students to make the sketch first, just reading the question, make a sketch of the answer, of what the question is about. This is what you should be able to do. We have y equals ln of x, this graph here, which intersects at the point 1, 0. ln of 1 equals 0. So it's the point 1, 0. And among all the tangent lines, we are looking for the tangent line that also happens to go through the origin. There's only one of them. The tangent line, for example, at this point here, would look somewhat like that, and it's definitely not going through the origin. So how can we find the equation of this tangent line that goes through the origin? The great idea in this exercise is to realize that there's 2 ways to describe what the slope of this line is. The first way is to think in terms of derivatives. That's what we've been doing all year. What's the derivative of y equals ln of x? It's 1 over x. So at that special point, a ln of a, this is a, the slope is 1 over a. But we can also think of the slope of this line in a different way. We can say, hey, look, I have 2 points, so I can do rise over run, just what I've learned in Algebra 1. And if you do rise over run between 0, 0 and a ln of a, you get that the slope is ln of a minus 0 over a minus 0. So it's ln of a over a. This and that are the slope of the function, of the line. But we're talking about the same line, so these two need to be equal. There's no other way. Since it's the same line, it only has one slope. So these two results must be equal since we are studying the same line. So I can set up 1 over a equals ln of a over a. And that means we can just focus on the numerator, that 1 has to be ln of a. And therefore, a equals e. Then I can plug it back in and find that the point is E1. So that point right here is E, which is 2.7 and 1 up. A very neat exercise. thinking about using the slope in two different ways, rise over run and the derivative, and combining these two ways allow us to find the answer. All right, last thing, the domain of a function always restricts the domain of the derivative. No big deal, but this is a good example. If f of x equals ln of x, the graph is like this. We just saw that. When I look at the derivative, f prime, let me just change the color if I can. No, I can't. The derivative of f of x equals ln of x is 1 over x. So what does that look like? 1 over x is something like that. Okay. Oops. I don't know why I did that. Oops. But then this entire place is actually telling us something about the slope, but the slope doesn't exist because ln of x is completely absent from here. So we shouldn't, when we look for the derivative of ln of x, we should actually not consider this part. This is not in the domain because it doesn't describe anything. Ln of x is here only on the positive side, so this is the only place that the derivative should exist. All right. So that concludes 3.4, which is the last of the big derivative rules, and now we can pretty much differentiate any function that we can come up with. Thank you so much for listening again.